In this part of the chapter, we are going to be looking at trigonometric functions, which are functions that accept angles as their input. And there are 6 trigonometric functions that we are going to be exploring. They are the sine function, the cosine function, the tangent function, the cosecant function, the secant function, and the cotangent function. And of these 6 functions, 3 of them are inside our calculator. They are the sine, cosine, and the tangent functions. And they are here. Sine, cosine, tangent. So for example, if I were to trigger the cosine function and I input a 60 degrees into the cosine function, it will give us a calculated value of 1 over 2. So how are the values being calculated? Let me give you a quick insight into the calculation. And I'm going to do that by referencing it to a simple right-angled triangle. So if I have a right-angled triangle, which means that for this triangle, one of the angles is going to be 90 degrees. And if I were to call the length here as x, the length here, I'm going to call it y, and this length, I'm going to go for an r. So based on this triangle, we can actually see how sine, cosine, tangent, and the other 3 functions are being defined. Because for a sine function, if I were to let the angle be this angle over here, so this is going to be theta. So sine of this angle theta is defined as y over r. So this length over r. And cosine of this same angle here is defined as x over r. So this is going to be this over this. And tangent of this angle is defined as y over x. So this over this, okay, which is sort of like not that easy to memorize, but it is in our syllabus and I really need you guys to memorize. So there are different ways to memorize this. So I'm going to share with you one that I have learned when I was in my secondary school, and that is actually using a more Singapore dialect kind of acronym. It is this acronym called the Topical, which is this Toa, T-O-A, Ka, C-A-H, so S-O-H, Topical. So Toa is for T, tangent, and to calculate for tangent of an angle, it is opposite over the adjacent. Y over x, opposite over the adjacent. We are talking about the line, the length that is opposite the angle and the length that is adjacent to the angle. So Toa, opposite over adjacent. Ka, C, it is for cosine, and cosine is going to be adjacent over h. H is the hypotenuse. So it's going to be x over r, adjacent over the hypotenuse. And so S is for sine, and it is calculated as opposite over the hypotenuse. So opposite over the hypotenuse, y over r. So this makes my job easier in terms of memorizing the definition for sine, cosine, and tangent. As for the other 3 functions, they actually derived from these 3, which is cosecant theta. Cosecant theta is defined as 1 over sine theta. And secant theta is defined as 1 over cosine theta. And cotangent, the last one, cotangent theta is defined as 1 over tangent. So this cotangent theta is defined as 1 over tangent theta, which means if sine theta is y over r, 1 over sine theta is 1 over y over r, which is going to be equal to r over y, and this is 1 over this, which is equal to r over x, and this is 1 over y over x, it is x over y. So for example, how can we apply this? Okay, let me give you a simpler scenario to just get us more warm up to the trigonometric function. So let's say I have a right-angled triangle, and for this right-angled triangle here, this side is 1, this side is 1. And if I were to do a Pythagoras theorem to find the length of the hypotenuse, it is going to be square root of 1 square plus 1 square, which is going to be square root of 2. So let's say I'm looking at a triangle that is like this, and I'm curious to find out what is this angle here. And of course, okay, if you were to use geometry, you can see that this is an isosceles triangle. So if this is 90 degrees, then this angle and this angle, they must be 45 degrees. So we do know that this is 45 degrees, okay? But what if we want to make use of trigonometric function to calculate for this angle instead of using geometry that we have learned to calculate that this is 45 degree, let's see whether the trigonometric function can also lead us to a 45 degree. So for this scenario here, I can use either of these three functions. Let's say, let's use cosine, okay? So if I were to use cosine, then I know cosine of this angle, car, is going to be adjacent over the hypotenuse. So it's going to be 1 over square root of 2. In order for me to find theta, we need to reverse the effect of cosine. And to reverse the effect of cosine, the notation is this. Cosine inverse, okay? This notation here represents the reversal of the cosine function, which means that for sine, it will be sine inverse. For tangent, it is going to be tangent inverse. And the notation for sine, it is going to be this. Sine inverse, the notation for tangent is going to be this, tangent inverse. So for cosine, it is going to be cosine inverse of 1 over square root of 2. In fact, this will actually help us to calculate the value for cosine, and this can be done by using our calculator. Let me show you how that can be done. So on the calculator, what we will do is we want to trigger cosine inverse, and cosine inverse is actually here. So here, shift cosine, and I'm doing a cosine inverse of 1 over square root of 2. So let's press in 1 over square root of 2 here, 1 over, then we have a square root of 2. Calculating for this, it actually gives us an angle of 45 degrees, which was what we have already calculated it to be. And even if I have a slightly more complicated scenario, okay, which geometrically I will not be able to do good calculations like this. For example, what if I were to change the length of the sides to, let's say, how about 3? Okay, what if I were to change this to 3 and I were to go for this as 4? So 3, 4, if I were to make use of the Pythagoras theorem, then it is going to be equal to square root of 3 square plus 4 square, it is going to be square root of 25. So square root of 25 is 5, so the length of the hypotenuse here is equal to 5. And now we will not be able to use geometry to predict the value of theta. We are going to make use of the trigonometric function. We can choose either of the functions. So let's say we are going to go for, how about let's go for the sine function. So if I were to go for the sine function, we know sine of this angle, okay, because this is the value of this is the value that I'm interested in. So I'm going to go for sine of this angle. Sine of this angle, so it's going to be opposite over the hypotenuse. So it's going to be 3 over 5, which means that theta is going to be equal to sine inverse of 3 over 5. Let's see what is the angle. So we're going to do a sine inverse. So shift sine, which will give us sine inverse of 3 over 5. And this gives us a 36.9 degrees. So this is 36.9 degrees, okay? We are seeing a simple but good usage for trigonometric function. So it gives us access to angles which prior to this, it may not be that easy for us to do the calculations for. So if you were to look at this, okay, I just want to point out something in terms of the notation, because later on in the chapter, we will find out that there are more notations that are related to this sine, cosine, tangent, and the other three also. For example, notation like this. Okay, if I were to write sine 2 theta, this 2 here is actually trying to tell us that sine theta is going to be multiplied by itself, so it's going to be the same as sine theta square. It's going to be sine theta times sine theta. So this is pronounced as also sine square theta. But this can be sort of like confusing if we were to just try to impose this notation to this. Because when we talk about sine this theta, okay, this is pronounced as sine inverse. And sine inverse is trying to reverse the effect of the sine function. It is not actually trying to do this. It is not actually trying to do a sine theta to the power of minus 1. Because if it is sine theta to the power of minus 1, it is not trying to reverse the effect of the sine function. It is trying to do a reciprocal to the sine function. It is 1 over sine theta. So this is actually not the same as this. So notation-wise, yes, I feel that it is confusing, and I think mathematicians has also feel that this is sort of confusing. That was why they have invented another notation to avoid applying this negative power thing. Okay, the moment when it is this negative power, it represents for a trigonometric function the inverse function. So when we actually need a negative power, the inverse function is not a power, okay? This is inversing. But when we actually need a negative power, then instead of writing as a negative power, we can definitely write it as this, or we can also write it as this, which is cosecant theta. This will help us to avoid using this in our working, which actually simplifies things a lot, especially if you start to get familiar with the notations for all the trigonometric function. It will be really way simpler and smoother if we were to stick to the cosecant theta function, which represents the reciprocal of sine, which is 1 over sine, instead of trying to apply negative power. Okay, which means that if I were to write it as cosecant square theta, it represents 1 over sine square theta. I don't have to write this as sine minus 2 theta. Okay, and this is very, very seldom used. We don't even use it at all. So I just want you to, even if you find this a bit more confusing now, I want you to memorize this first, and I believe that along the way, when we are more used to the notation, it should become clear for most of us, okay? So let's take note. This is called sine inverse. It is not sine to the power of minus 1. And sine to the power of minus 1, if we really need to write this, we should write it as either 1 over sine, or even better, let's make sure that we write it as cosecant theta. Okay, and since we are talking about angles, I also want to mention one more thing, which is that angles, there's actually another unit of measurements. We have been using degree to measure angles. There's actually another one, that is the radians unit of measurement. Radians is another way for us to measure angles. And let me show you how a radian is being defined. Let's look at what is representing 1 radian. And we are going to look at it based on geometry. So if we have a circle, and if we were to draw a sector such that the radius of the circle is r, such that the arc length of this sector here is also of a length of r, then this angle here is considered as 1 radian, which the notation or symbol wise, it is this 1 radian, R-A-D. Or it is also very common for angles, which is expressed in terms of radians, to totally eliminate the usage of radian, which means that if I were to know that there's this angle theta and it is 1 radian, we can just simply write it as 1. And it is going to be automatically interpreted as radian. But of course, if this were to be degree, then please make sure that you write in the degree notation so that it will not be confused as 1 radian, which means that for degree, we need to write the degree all the time. But for radian, we can either choose not to write anything at all if it is represented in terms of radian, or we can definitely write it as this 1 radian. So if r as the arc length represents 1 radian, that means 1 unit of arc length will represent 1 over r radian. So if I were to go for the entire circle as the arc length, what is the arc length of the entire circle? It is the circumference of the circle, and that is 2 pi r. This will be 1 over r times 2 pi r radians, which is equal to 2 pi, which means that 2 pi actually represents the angle for the entire circle. And what is the angle for the entire circle? 360 degrees. That is why 360 degrees is going to be representing 2 pi. They are in fact exactly the same, okay? This is going to be in degree, this is going to be in terms of radians. So 360 degrees is the same as 2 pi radians, which means that 180 degrees dividing by 2 is going to be pi radians, which also means that if it is 90 degrees dividing by 2 again, it is going to be pi over 2 radians, which is what I wrote here. And I believe that it is going to be useful if you can just memorize this, okay? Because very often we will be required to convert an angle from degree to radian or radians to degree. For example, if we want to try to convert 60 degrees, okay? We want to convert 60 degrees to radians. Let's see what is going to be 60 degrees, okay, in radians. So let me pick one of them. Let's say I pick this, okay. So by using proportion, I know 360 degrees is going to be 2 pi radians, which means that 1 degree is going to be 2 pi divided by 360. So if we were to be interested in converting 60 degrees into radians, this is going to be, we can simplify this. This is pi over 180. So it's going to be pi over 180 multiplied by 60. So multiply by 60, multiply by 60. This gives me pi over 3 radians. And I also want to numerically show you that 60 degrees is equal to pi over 3. By making use of our calculator, we can actually try to do a quick calculation for let's pick one of the functions. Okay, so we have sine, we have cosine, we have tangent, and the other three which are derived from sine, cosine, tangent. Let's just go for, let's say, cosine. So let's see what is cosine of 60 degrees. We have actually looked at it just now. It is going to be equal to half. Okay, so cosine 60 degrees is half. Let's see whether we are going to be getting half if we were to do a cosine of pi over 3 radians. And to do that, I just want to bring your attention to this little symbol over here. This represents degree. It is a simple D, so it represents degree. I'm going to try change this into radians. So I'm going to go to setup on my calculator, and there's degree, there's radians. So I'm going to go for radians, number 4. So you realize that this little D symbol is now R. So the whole calculator's function is now calculating all angles which are going to be input into the trigonometric functions in radians. Which means if I were to press cosine again, this time in order for me to put in a 60 degrees, I'm going to try to put in a pi over 3 radians. Let's see whether it is going to be the same. Okay, we found out it was half just now. Let's see whether it is still going to be equal to half. So it's going to be pi over 3. This is equal to half. So our calculation, at least for the numerical verification that we have so far, it has justified to me that 60 degrees is equal to pi over 3. What if I want to look at what is 30 degrees? Okay, what is 30 degrees? So 1 degree is pi over 180. So 30 degrees is going to be equal to pi over 180 multiplied by 30. This is equal to pi over 6. A little homework for you. You can try to press this into the calculator. For example, doing a tangent 30 degrees and then changing it to the radians mode. Check whether it is going to give you the same thing if you have to do a tangent of pi over 6. And because if we were to be, okay, let me just change this back to degree first, okay? If we were to be pressing for cosine, sine, tangent of angles. For example, let's say we try tangent. If we were to do a tangent of, let's say, 68 degrees, okay, I'm in degree, so let's say tangent of 68 degrees, I will get this number, 2.4750868853, and so on. These are probably irrational numbers, and it is very often for us to be seeing irrational numbers when we try to input different angles into the trigonometric function. But in our syllabus, there are actually some special angles where we are expected to know their exact values. That means we cannot just simply press into the calculator. We need to memorize the result when these angles goes into the trigonometric functions. And they are actually these few angles here. We call them the special angles, which we are supposed to memorize them. Okay, let me explain to you what are the special angles. So the special angles are actually just these 5 angles: 0 degrees, 30 degrees, 60 degrees, 45 degrees, and 90 degrees. I've already converted them into radians. So 0 degrees is 0 radians, 30 degrees is pi over 6. We have look at it just now. 60 degrees is pi over 3, and 45 degree, you can do your conversion, it is pi over 4, and 90 degrees, we did a conversion also, it is pi over 2, or you can definitely just refer back to here, it is pi over 2. So we have these few numbers which are the result of, for example, 30 degrees, when we do a sine 30 degrees, this is the result, 1 over 2. When we do a cosine of pi over 4, the result is 1 over square root of 2. And we're not going to press this into the calculator, although we can. Our aim in terms of us encountering special angles in our exam is so that we can quote the exact value. Because if we were to press it into the calculator, we will not be getting a 1 over square root of 2. We will be getting 0.7 something, 0.70 something. So we don't want that, okay? Because usually when it comes to special angles, the question will ask us to produce the numbers, the result in exact form. So you do want to make sure that you memorize this entire table. I think for 0 degrees and 90 degrees, I mean, first of all, they are easy. The numbers are easy. If you were to press into your calculator tangent 90 degrees, you'll realize that you're not going to get any solution. That is why you will not be required to memorize this. It is undefined anyway. So for this 0, 1, 0, 1, 0, which is for this sine, cosine, and tangent, I think to memorize this, I mean, of course, you can memorize, or you can just simply press into your calculator. Okay, but the one that are harder will probably be this 9 over here. So for this 9 over here, again, there are different ways where students there are different ways students will find to memorize these 9 results. But the one that I have learned, which I thought it was very useful, was the one that I learned from my secondary school's teacher, and that is by drawing triangles. In fact, there are just 2 triangles that I need to memorize, and I'm going to derive all these results based on the triangle. So the 2 triangles are here. Let me show you how we can actually make use of these 2 triangles to derive sine, cosine, tangent of the 3 special angles, which are the 30 degrees, 60 degrees, and 45 degrees. So the first triangle is going to be the triangle that will help me to deal with 30 degrees and 60 degrees, or pi over 6, which is the radians form of 30 degrees, or pi over 3, which is the radians form of 60 degrees. So since we are talking about 60 degrees, 30 degrees, the triangle that I'm going to be making use of will be an equilateral triangle. So what my teacher taught me was to first draw an equilateral triangle so that we can have 60 degrees, 60 degrees, and 60 degrees. But from one of the vertex of the equilateral triangle, I am going to draw a perpendicular bisector to the base. And because this is an isosceles triangle also, drawing a perpendicular bisector to the base, to the vertex, will also cause this angle to be bisected. So this angle is going to be the same as this angle. And since total it is 60 degrees, dividing it by 2, this gives me a 30 degrees and 30 degrees. And I'm going to give the smallest integer value that can be used to represent the length, and nice numbers, okay, integer values that can represent the length of the triangles that I see here. So I'm going to go for 2 here, 2 here, and 2 here, but because it is bisected, so it's going to be 1, 1. So based on this triangle, we can then deduce sine of 60 degrees, because sine is so sine is SOH, opposite over the hypotenuse. What is the opposite side? Okay, for the opposite side, since it belongs to a right-angled triangle, we can also feel the length of the opposite side by making use of the Pythagoras theorem. It is going to be square root of 2 square minus 1 square. So this is going to be square root of 3, which means that sine 60 degrees is going to be square root of 3 over 2, opposite over the hypotenuse. So this is going to be square root of 3 over 2. How about cosine 60 degrees? Cosine 60 degrees, C-A-H. So adjacent over the hypotenuse, it is 1 over 2. And tangent of 60 degrees, TOA. So T-O-A. So T, tangent, O, opposite over the adjacent. So it's going to be square root of 3 over 1. So based on this, I've already deduced this set of numbers. Okay, it is like really easy, right? So I can also make use of this to deduce, of course, sine 30 degrees, because we also have a nice 30 degrees in this triangle with good and nice integer sides. So 30 degrees, sine 30 degrees is opposite over the hypotenuse. It is 1 over 2. And cosine of 30 degrees is adjacent over the hypotenuse. Adjacent is square root of 3 over hypotenuse, which is 2. And tangent of 30 degrees is opposite over the adjacent. So it's 1 over square root of 3. So this triangle, this one single triangle, when I divide it properly, it helps me to settle both the 30 degrees and the 60 degrees. And Another triangle that will also help me is to deal with this 45 degrees or pi over 4 radians. So we need a triangle that has 45 degrees. In fact, we look at one such triangle just now. It is a right-angled triangle where the two sides of the right-angled triangles are the same. So we are looking at an isosceles triangle. So because when this happens, I know this is going to be 45 degrees. I know this is going to be 45 degrees. 45 degrees is like pi over 4 radians. So this is also going to be pi over 4. And I'm going to go for a nice integer number for this side and this side. And I'm going to go for the smallest possible one. I'm going to go for 1, 1. Which means that if I were to apply the Pythagoras theorem, this is going to be square root of 1 square plus 1 square, it is going to be square root of 2. So based on this, we can then find out what is going to be sine of 45 degrees or sine of pi over 4. Sine of pi over 4 is opposite over the hypotenuse, is 1 over square root of 2. And cosine of pi over 4, similarly, adjacent over the hypotenuse, it is also 1 over square root of 2. And tangent of pi over 4 is going to be opposite over the adjacent, so it's going to be 1 over 1, it is equal to 1. These are the special angles that you should memorize. And since we talk about angles, we also know that angles can be either acute angles, which are angles that are between 0 to 90 degrees. They can also be obtuse angle, which are angles that are bigger than 90 degrees but less than 180 degrees. And we can also talk about reflex angles. Reflex angles will be angles that are more than 180 degrees. All these angles can be input into a trigonometric function. But let me show you something, okay? When I input angles into the trigonometric function, let's say I choose sine. If I were to insert an acute angle, for example, 42 degrees, okay, I'm in the degrees mode. So if I were to do a sine 42 degrees, I'm going to get this 0.669 and so on. Okay, it is a positive number. But let me show you what happens if I were to insert a reflex angle. So if I were to insert a reflex angle, so let's say it must be an angle that is bigger than 180 degrees. So let's say 195 degrees. Okay, if we were to insert this in, it is actually going to give me a negative value. And this won't be captured by making use of a simple right-angled triangle, because if we were to be using all the length that we were talking about just now, they were supposed to be giving me positive numbers. So which means that the right-angled triangle that we have just discussed gives us a good insight, but it is not going to give us the complete insight to how sine, cosine, tangent are going to be calculated. So I'm going to go into the details of how this is done. Let me show you. Previously, we have made use of a right-angled triangle to get a glimpse of how the sine, cosine, and tangent function process the angle. But when we look at it from the perspective of a right-angled triangle, we are limited to seeing angles based on just acute angles. So our perception is limited. We know, like what we have just talked about, they are also going to be obtuse angle, they are also going to be reflex angle. So an even better way for us to perceive angles so that we can take into account of all sorts of angles is to see angles on an XY axis. So if I were to draw for us an XY axis, let's say it is this here, this is going to be the x-axis, this is going to be the y-axis. Let me introduce to you a convention of how we can be representing angles on an xy axis. So let's say I want to represent 45 degrees. So to represent a 45 degrees on an xy axis, what we will do is we will represent it by this angle here. And why is it that it is specifically this angle here? Because the sine convention or the angle convention on an xy axis indicates that we will always reference the angle, let's say 45 degrees, we will always reference the angle first from the positive x-axis. So this is the positive x-axis, this is the negative x-axis. So we will start referencing angle from the positive x-axis, which is going to be here. So from here to here, this angle will be 45 degrees. And because we are trying to reference everything to the positive x-axis, so we can also try to take into account of not just angles that are turning this way, we can also take into account of angles that are turning this way. And the convention is this: if I were to start from the positive x-axis and if I were to define an angle that is based on me turning in an anti-clockwise direction, then the angle will be positive angle, a positive 45 degree. But if we were to try to reference an angle which will require me to turn at a clockwise direction, so for example, I'm also going to try to represent 45 degrees, but it is for this line instead of this, which means that the way that I turn has to be in a clockwise direction. Then this angle will be a negative angle, negative 45 degrees, which means that by making use of the same convention, I will also be able to indicate angles like this. Let's say this angle here is 135 degrees. I will also be able to indicate angles like, for example, this. And this, let's say here, I'm indicating a minus 120 degrees. And based on this sign convention, based on this angle convention, we will then be able to capture the full essence of how sine, cosine, tangent, and the derived cosecant, secant, and cotangent is going to be calculated, and why sometimes you're going to be getting a positive number, why sometimes you're going to be getting a negative number. Let me show you how that can be done once we have gotten this sign convention, we have gotten this angle conventions sorted out. So by making use of the same angle convention, let's say I have this, okay? So we have our y-axis here, we have x-axis here. Let's say I'm going to deal with an acute angle. And I'm going to show you for an acute angle whether sine, cosine, tangent are going to be positive or negative. So I'm going to do that by poking a point in this quadrant of the xy axis, and this quadrant is called the first quadrant, so I'm going to put it as Q1. Okay, let me just give you all the quadrants. Okay, so this quadrant, it is called the first quadrant, quadrant 1. This is called the second quadrant, so quadrant 2. This is going to be the third quadrant, so quadrant 3, and this is the fourth quadrant. This is quadrant number 4. So for the first quadrant, if I were to put a point, any point that is in the first quadrant, then this will have a positive x and positive y as the coordinate for that point. And if I were to then draw a triangle starting from the origin to this point and dropping it down here will give me a right-angled triangle, and referencing the length to the coordinates, I know I'm going to be having a positive x and a positive y, and the angle, I'm going to go for this particular angle here, and since I'm going in the anti-clockwise direction, I'm looking at this as a positive angle theta. And based on this positive angle theta, we can then come out with sine of this angle, cosine of this angle, and tangent of this angle. Let's see what it is going to be. So for the sine of this angle, sine, so opposite over the hypotenuse. So opposite is y, and the hypotenuse is this, which is going to be square root of x squared plus y squared. The hypotenuse for my angle convention, when I draw this triangle here, it is always going to be a positive number, regardless of the quadrant that it is in. Okay, so if it is a positive number, then sine is going to be equal to opposite over the hypotenuse, so it's y over r. It is a positive number, so this is going to be bigger than 0, and cosine is going to be x over r. This is also bigger than 0, and tangent is going to be y over x. This is also bigger than 0 since x and y are positive numbers. But if I were to now progress to the second quadrant, if I were to progress to the second quadrant, so let's say I poke another point here, and if x and y are positive numbers, then the coordinates of this will be minus x and positive y. Okay, because here we have negative x, and here we have positive y. And if I were to draw a triangle again in the same way as this, and this is 90 degrees here, then what we have, if I were to make use of the xy coordinate of this point to indicate the two lengths, this is going to be minus x, and this is going to be positive y. And the angle is going to be this, an obtuse angle. I'm going to call this angle here theta. This is an obtuse angle. And for this particular angle, this angle which is obtuse on my diagram, if we were to try do a sine of this angle, sine theta. Sine theta is going to be the same thing. opposite over the hypotenuse. Opposite is y, which is a positive number. The hypotenuse is going to be square root of negative x squared plus y squared. Is going to be square root of x squared plus y squared, and I'm going to just represent it by r. Again, it is going to be a positive number. So sine is going to be equal to opposite, which is y, over the hypotenuse, which is r. So sine is going to be a positive number. As for cosine theta is going to be adjacent over the hypotenuse. So it's going to be minus x over r, and this will start to become negative. And as for tangent of this is going to be equal to opposite over the adjacent, so y over minus x, and this is also going to be less than 0. We can very quickly verify this by once again making use of our calculator. Let's say we go for an obtuse angle, for example, let's say 120 degrees. So let's check sine of 120 degrees. Let's see whether it is like what we have predicted, a positive number. So sine 120 degrees is positive. How about cosine? Cosine 120 degrees. Cosine of 120 degrees, according to our prediction, it should be negative. Let's see. So cosine of 120 degrees is negative half. It is a negative number. How about tangent? Tangent of 120 degrees, it should be negative. Tangent of 120 degrees is a negative number. So it goes according to our prediction. Let's try the same thing for an angle that is in the third quadrant and in the fourth quadrant. So for an angle that is in the third quadrant, I'm going to poke a point, let's say here. And if I were to draw the triangle in the same way as this is going to be at minus x and minus y. Minus x and minus y, okay? Because it is in the negative x-axis region and the negative y-axis region. As for the angle, now we are going to be looking at an angle that will turn all the way until here. So we are looking at an angle that is like bigger than 180 degrees. It is a reflex angle, so something that is like maybe 200 degrees. So we are working on that kind of angle. And how do I calculate for the sine of this particular angle? Sine of this angle is going to be equal to, okay, so it's going to be opposite over the hypotenuse. So what is the opposite? The y coordinate will give me the inspiration for the opposite. It is going to be minus y. The adjacent is going to be from the x coordinate, it is minus x, and here is going to be a positive number, which is going to be square root of x squared plus y squared. I'm going to once again represent it by a positive number r. So sine is going to be opposite over the hypotenuse, so minus y over r. This is going to be negative. Cosine of this is going to be adjacent over the hypotenuse, so minus x over r. This is negative. And tangent theta is going to be opposite over the adjacent, so it's minus y over minus x. It is positive y over positive x. This is bigger than 0. So from what we have seen so far, in the first quadrant, all are positive. In the second quadrant, the sine is positive, and in the third quadrant, tangent is positive. Can you guess which is going to be positive in the last quadrant? Is it really going to be cosine theta? Let's try. So in the last quadrant, I'm going to poke a point here again, and its coordinate is going to be positive x and minus y. So if I were to draw a right-angled triangle once again, so this is right angle, and the hypotenuse here is going to be r, this is going to be minus y. The angle, this time theta, is going to go all the way to here. Okay, so this is going to be the angle that we are dealing with. So for sine of this angle all the way till here, sine of this angle is going to be opposite over the hypotenuse. So opposite is minus y. The hypotenuse is a positive number r, and this is less than 0. Cosine theta is adjacent over the hypotenuse, so it's x over r, and this is indeed positive. And for tangent theta is going to be the opposite over the adjacent, so it's minus y over x. This is less than 0. So like what we have predicted, cosine theta is positive when I'm dealing with an angle theta that is in the fourth quadrant. Again, there are acronyms for us to memorize which of the functions when the angles, which of the functions will be positive or negative when we are dealing with angles that is going to go into different quadrants. And the one that I have memorized is actually this thing called add sugar to coffee. Okay, there are really a lot of versions out there, but I like this add sugar to coffee. I like coffee. So add sugar to coffee, how are we going to be using them? Okay, it is this this ASTC thing, add sugar to coffee. So A is going to be in the first quadrant, add sugar, A. A means all are positive. Sugar means sign is positive. Coffee means, sorry, not coffee, add sugar to coffee, so T. T means tangent is positive. And finally, C means cosine is positive. Add sugar to coffee, ASTC. All the trigonometric functions gives me positive values when I try to go for an acute angle that is in the first quadrant. Sine is positive, tangent is positive, and cosine is positive if I were to be going all the way for an angle that is going to all go into the fourth quadrant. Let us take a look at some questions to see how this quadrant thing and maybe some of the things that we've discussed previously can be applied. Let's take a look at these two questions here. So let's take a look at question number 1. In question number 1, we are given that sine theta is 3/5 and tangent theta is less than 0. The first thing that we want to know is which quadrant is this angle theta in. So if I were to just do a quick sketch of the x-axis and the y-axis, sine theta is 3/5, which means that sine theta is positive. According to what we have discussed, when will sine theta be positive? Add sugar to coffee, the first quadrant and the second quadrant. So for sine theta to be positive, it is going to be either here or here. And according to the question, tangent theta is negative. So according to add sugar to coffee, which angles when I do a tangent of the angle is going to be negative? It is going to be negative in the second quadrant and the fourth quadrant. Tangent is going to be negative. So where do you think is the angle theta? The angle theta is going to be in the second quadrant. Because when I do a sine of an angle that is in the second quadrant, it's going to give me a positive number. And when I do a tangent of an angle that is in the second quadrant, it's going to be a negative number. So the angle is going to be here. I'm going to draw my triangle this way. And this is going to be the angle theta. And we know, according to what this question says, sine theta is, according to the question, 3/5. So what we need to do next is to fill in the sides of this triangle. So for the sides, this I can see is opposite over the hypotenuse. So opposite here is 3. The hypotenuse here is going to be equal to 5. And if I were to do a Pythagoras theorem to find this, this is going to be square root of 5 squared minus 3 squared. It is square root of 16. This is equal to 4. So should I fill in 4 here? No. That's the power of us trying to represent the angle on an xy axis, because the length, whether it is positive or negative, can be captured very easily by looking at it in the different quadrant. So for this, it is positive because it is on the positive y axis. And for this line here, yes, I know its length is 4, but I'm going to represent it as minus 4. Why? Because it is on the negative x-axis. So now we have our triangle. And we are ready to then find out what is cosine theta. Cosine theta is going to be adjacent over the hypotenuse, so it's minus 4/5. Next, in question number 2, we are given that cotangent theta is equal to minus 7/3. Let me write it down. So cotangent theta, this is minus 7/3. What is cotangent theta? Cotangent theta is the reciprocal of tangent. So according to what we have discussed, cotangent theta will lead us to finding what is tangent theta, which is going to be 1 over minus 7/3. So tangent theta is minus 3/7. If cotangent theta is minus 7/3, tangent theta is minus 3/7, which means that tangent of this angle, which we are trying to capture, is giving me a negative number. So when will tangent give us a negative number? Let's come back to our add sugar to coffee again. So based on add sugar to coffee, tangent will be negative when it is in the second quadrant or the fourth quadrant, because tangent will be positive in the first quadrant and the third quadrant. So these are the two quadrants where tangent is going to be negative. And according to what this question says, let's see this other piece of information that is given. Sine is going to be negative. So if sine is negative, okay, let's look at our add sugar to coffee, okay? Sine is negative. So when is sine negative? Sine will be negative here and here because this is where sine is positive, this sine is positive. So sine is negative in here and here. So it's going to be here, here where sine is going to be negative, which means that we are looking at an angle that is going to be in the fourth quadrant. Let's now try to solve for cosecant theta. Cosecant theta is 1 over sine theta. So let's draw the triangle first. The triangle is going to be this, and the angle is going to be this. And we are given by the question that tangent of this angle theta is minus 3 over 7. So tangent is opposite over the adjacent. So we know that it is going to be 3 here and 7 here. This 7 is fine because it is at the positive x-axis, but this 3 is on the negative y-axis. So this negative should be assigned to minus 3. So I can in a way see this as if it is minus 3 over 7. And we're going to do a Pythagoras theorem to find the hypotenuse, which is always going to be positive. So it's going to be square root of 7 square plus minus 3 square. So it's going to be 49 plus 9. It is going to be square root of 58. So we know this is going to be square root of 58. And what the question wants us to do is to find cosecant theta. Cosecant theta is 1 over sine theta. So it's 1 over, how do we calculate sine theta? Opposite over the hypotenuse. So it's going to be opposite over the hypotenuse, so it's minus 3 over square root of 58, which means that cosecant theta is going to be minus square root of 58 over 3. There's still another table that I do want you to memorize. Yes, I know there are a lot of things to memorize here, but after a while you will realize that they can also be very easily derived. Like for example, this huge table that I'm showing you here, once you have gone through another part of this chapter called identities, you can actually make use of them to derive quite a few of the results here, okay? But for now, let's just make it a point to memorize this. I have given you the results based on degrees and the corresponding radians, okay? Because 180 degrees is also pi radians, okay? In case you have forgotten, we'll talk about it here. 180 degrees is pi radians. So they are actually representing the same transformation, okay? This is, we are talking about at least to show us all the trigonometric transformations through the angle, through the different angles. So for example, if I were to see a sine 180 degrees minus 30, it is the same as sine 30. Okay, I can very quickly show you sine 180 degrees minus 30. Okay, let me just write it down here. So sine 180 degrees minus 30 degrees. Let's see whether it is really equal to sine 30 degrees. So let's try. On our calculator, we are in the degree mode because here is D. So let's try to press a sine 180 minus away 30 degrees. 180 degrees minus 30 degrees, we get a half. Okay, let's see whether it is the same as sine 30 degrees. It should be, because you know why? Sine 30 degrees is a special angle and I have to memorize it. I know sine 30 degrees is half, but let's still press it into the calculator. Sine 30, this is equal to half. Okay, so just memorize this, memorize this, memorize this. I'm going to show you some application. And of course, after we have learned the part of this chapter on identities, trigonometric identities, we can come back here again, or you can have it as your homework to see how you can make use of trigonometric identities to prove why this is equal to this is equal to this, and so on. Okay, but this we can actually prove it today, this and this. Okay, for the rest, I will just ask you to go and memorize it for now. But for these two, we can sort of like discuss about it. Let's take a look at first the complementary angles. So for complementary angles, we will look at it as angles in a right-angled triangle. So let's say here I have a 90 degrees. This is X, this is Y, this is R. And I'm going to call this angle here theta, which makes this particular angle here 90 degrees minus theta. 90 degrees minus theta. Okay, so that the total angle is equal to 180 degrees. So if I were to now look at this, sine 90 degrees minus theta, I'm going to prove to you why this is equal to cosine theta. So for sine 90 degrees minus theta. What is sine 90 degrees minus theta? It is the opposite over the hypotenuse. So this is x over r. And do you know what is also x over r? When we try to do a cosine. When we do a cosine of theta. Cosine of theta is equal to, cosine of theta is x over r, the adjacent over the hypotenuse. So this is also x over r, which means that this is the same as cosine theta, which is the first complementary angle result that we have here. Sine 90 degrees minus theta is cosine theta, or if it is in radians, sine pi over 2 minus theta radians, pi over 2 is 90 degrees, sine pi over 2 minus theta radians is equal to cosine theta. We can make use of the same strategy to prove the rest. So let's say I'm looking at cosine 90 degrees minus theta. Let's see what it is going to be. So cosine 90 degrees minus theta. Cosine 90 degrees minus theta, adjacent over the hypotenuse, this is equal to y over r. And if we were to do a tangent of 90 degrees minus theta, tangent of 90 degrees minus theta is going to be the opposite over the adjacent, so it's going to be x over y. How about sine theta? What is sine theta? Sine theta is opposite over the hypotenuse, so this is y over r. And how about tangent theta? Tangent theta is opposite over the adjacent, so this is y over x. So now let's try to match again, okay? Y over r, that's why I know this is equal to sine theta, which gives us our second result here. Cosine 90 degrees minus theta is sine theta. And finally, x over y is the reciprocal of this. So x over y is like 1 over y over x, because 1 over y over x is equal to x over y, which means that we are looking at 1 over tangent theta. And what is 1 over tangent theta? It is cotangent theta, okay, which is this 1 over tangent theta. Let me write it down here instead. So this gives us a cotangent theta. Okay, that is the last result that we have here. Tangent 90 degrees minus theta is cotangent theta. This is even easier to explain. You know why? For example, if we were to do a sine 30 degrees plus, let's say I use this, okay? And k is integer value. Please take note, integer means it can be negative also. Okay, so it can be negative 2, it can be positive 1, it can be negative 3. So what if I have 360 degrees multiplied by positive 1? And according to what we are looking at here, this is the same as sine 30 degrees. I mean, obviously, right, if you were to look at it based on the xy axis, then where is 30 degrees? 30 degrees, maybe it is somewhere here, positive 30 degrees. How about where is 30 degrees plus 360 degrees? 360 degrees is making one full round. So we are talking about 30 degrees plus another 360 degrees, which comes back to exactly the same place. That is why 30 plus 360 degrees is actually physically representing the same angle, 30 degrees. That is why this is the same. Even if you were to plus another round of 360 degrees, it will still come back to sine 30 degrees, which means that even if you were to take this and multiply it by 2, multiply it by 3, it's still going to be equal to sine 30 degrees. Even if you were to multiply this by negative 1, if you were to multiply this by negative 1, negative angles, that means we are going to be going anti-clockwise. No, we are going to be going clockwise. So if we are going clockwise, 30 degrees is here. And if we are going clockwise, we are going one round and coming back to here. It is still going to be equal to 30 degrees. That is why regardless of whether you plus multiples of 30 degrees or plus multiples of 360 degrees or minus multiples of 360 degrees, you are still going to be getting back exactly the same angles. And what is 360 degrees? It is 2 pi radians. That is why whether you do a theta plus 2 pi or theta plus 2 pi times 2, 2 times of 2 pi is 360 degrees, it is still going to get back the same thing. Theta minus, for example, 4 pi. 4 pi is 2 times of 2 pi. It is still going to get you back the same thing because it is making one full round and coming back to the same angle. So to me, I feel that this is probably one of the easiest to remember because it clicks to the physical representation of the angle when you just go for one more full complete round, either anti-clockwise or clockwise. Okay, that is why it is still going to be the same angle. Let us take a look at some applications, some simple application. Let's take a look at this, question number 3. So in question number 3a, we are supposed to look at tangent of 270 degrees plus theta. And we want to try to express this in terms of sine theta, cosine theta, or tangent theta. So we're going to do an angle transformation so that we can hopefully change this to either sine, cosine, or tangent theta. Let's take a look at our table again. And sadly, we don't see a 270 degrees plus theta. So I'm going to give you some useful results, in fact just 2 of them, which are going to probably help us to do questions where we are looking at angle transformation, but the angle that are given are not exactly according to what we have memorized. So there are 2 cases here that I want you to further memorize. Okay, these are very, very useful results. They're not exactly angle transformation based on the trigonometric function, but they're just simple manipulation. For example, I have given you 270 degrees plus theta, which we can also change it to 360 degrees minus 90 degrees minus theta, because they are representing the same thing. 360 degrees minus 90 is 270 degrees, and minus times minus theta will give us a positive theta. So this is equivalent, okay? We didn't do any weird transformation, so they are algebraically the same. I'm going to make use of this and rewrite this as 360 degrees minus away 90 degrees minus theta. And what I'm going to do next is I'm going to make use of the transformation, because we have a 360 degrees minus theta. Tangent 360 degrees minus theta is minus tangent of theta. So tangent 360 degrees minus the angle is equal to minus tangent of the angle. So it is 90 degrees minus theta. And do we have a 90 degrees minus theta in our table? Yes, we have. It is here. So tangent 90 degrees minus theta is the same as cotangent of the angle. So this minus theta, is equal to cotangent of theta. Okay, according to what we have here. Tangent 90 degrees minus theta is cotangent theta. So this is minus is from here. This will become cotangent theta. Let's take a look at B. In B, we have a sine of minus theta minus 9 pi over 2. So the first thing that I'm going to try do is I'm going to try to remove this negative, okay? Because once again, I don't have something that look like this in the list that we have here, but we have this. Sine negative of an angle is equal to negative sine of the angle. So this is like seeing it as sine negative of this angle plus 9 pi over 2. So this is the same as negative sine of this angle. So here 9 pi over 2. And then in order for me to convert this to something that is like either sine, cosine, or tangent, I'm going to make use of this simple one that we talk about, because every time when I plus or minus 360 degrees, I'm going to get back the same thing. So I'm going to take this plus 9 pi over 2, and I'm going to minus 360 degrees, or if it is in radians, I'm going to minus 2 pi. So I minus 2 pi, it is going to be exactly the same as this, right? This minus 2 pi is just making one round back. It is going to be like exactly the same. So I'm going to apply that, and this is going to give me a minus sine of theta. 9 pi over 2 minus 2 pi gives me a 5 pi over 2. And I'm going to minus 2 pi again. So this is theta plus 5 pi over 2, and I'll minus 2 pi again because they are exactly the same. And now I have this, theta plus pi over 2. Theta plus pi over 2. And the reason, can you see the reason why I keep minusing away 2 pi? Because this 9 pi over 2 is way beyond 2 pi, which is 360 degrees. It is way beyond 360 degrees. So if I can just keep minusing away 2 pi or minusing away 360 degrees, I will be able to reduce the size of this 9 pi over 2 to at least something that is within 360 degrees, because all angles that we have memorized so far are within 360 degrees or within 2 pi, 0 to 2 pi. Okay, that is my motivation of why I did this and did this. I'm just trying to reduce this angle here to something that is between 0 to 2 pi, or to be between 0 to 360 degrees, since 2 pi is 360 degrees. And for this, I'm going to make use of another manipulation, and that manipulation is here. Okay, this is another useful manipulation that I want you to memorize, because 180 degrees minus 90 degrees is 90 degrees, minus theta is going to be equal to positive theta. So I'm going to make use of this. I'm going to rewrite this as pi minus pi over 2 minus theta. Okay, we are looking at radians, so I'm using this. Pi over 2 plus theta is pi minus pi over 2 minus theta. So pi minus away pi over 2 is pi over 2, and minus is positive theta. Okay, they are equivalent. So we now have this. And what is pi minus an angle? Pi minus an angle, we have it here. Let's see. It is going to be this. Okay, sine pi minus the angle is sine of the angle. So sine pi minus the angle is going to be sine of the angle, which is pi over 2 minus theta. And do we have a pi over 2 minus theta complementary angle? Pi over 2 minus theta. So sine pi over 2 minus theta is equal to cosine of the angle theta. And there's still some more questions that I want to try together with you. Let's take a look at how about this, 4a. In 4a, we are looking at trying to calculate for sine 210 degrees. So we need to be a bit creative here and think about how 210 degrees can be split up so that I can do a angle transformation. So the transformation will take into account of 180 degrees, 360 degrees, 90 degrees, all the angles are involving this field. So if that forms for me my inspiration, then I'm going to try to rewrite this as 180 degrees plus 30 degrees. Okay, this is what I mean by we do need to be a bit more creative, because what is 180 degrees plus an angle? Do we have it here? Yes, we have. Okay, so sine 180 degrees plus an angle is minus sine of the angle. So this is minus sine of the angle 30 degrees. And 30 degrees is a special angle. So what is sine 30 degrees? Sine 30 degrees is half. So this is equal to minus half. And the next one that we are looking at, let's see, is going to be this cotangent minus 7 pi over 3. So let's take a look at B. B, we have a cotangent of minus 7 pi over 3. And okay, I don't like to deal with cotangent because the transformations are all for sine, cosine, tangent, right? Except the complementary angle, but we also start with sine, cosine, tangent. So I do want to change this. I will change this to 1 over tangent of minus 7 pi over 3. Negative angle, I'm going to make use of a transformation. I'm going to make use of this particular transformation here. So tangent negative of an angle is negative tangent of the angle. So this can be written as 1 over minus tangent of the angle, 7 pi over 3. And now for 7 pi over 3, I'm going to attempt to split it up, or I'm going to attempt to do some transformation to it by making use of a bit of creativity. I'm going to rewrite 7 pi over, actually 7 pi over 3 is sort of big, right? It is bigger than 2 pi. So why not, okay? Why not, instead of splitting it up, I'm going to take 7 pi over 3 minus away 2 pi so that I can bring it into an angle that is between 0 to 2 pi. Bring it to an angle that is between 0 to 360 degrees. So this is going to be 1 over minus tangent of 7 pi over 3 minus 2 pi is going to give me a pi over 3. And again, pi over 3 is a special angle. I'm going to refer back to this list over here, or if you have already drawn the triangle, you can make use of the triangle to derive for yourself what is going to be tangent of pi over 3. Pi over 3 is like 60 degrees, so tangent of pi over 3 is square root of 3. So this is going to be minus 1 over, this is going to be square root of 3. that is all I have for this part of the chapter. It is quite a lot, but it is definitely going to form for us the correct kind of foundation that is necessary for us to proceed to the next few parts. So once you are ready, I'll see you in the next part.